Hello everyone, welcome to the April 27th edition of Calc 2. This is our last lecture where we're going to finish up section 10.5. Remember that you have WebAssign due on Friday, and the final exam / midterm will be taken on May 4th, which is the Monday of finals week. So today we're going to start off by finding the area between two curves. R equals 2 cosine theta, that's this curve, and r equals 2 sine theta, that's this curve. They should be the same size, but you get the idea. So we need to find the area of the region in between those two curves. That's this region right here. So we see that they're going to intersect right here, and that clearly occurs when 2 sine theta is equal to 2 cosine theta, which we know will happen at pi over 2. But now we want to find the area, so we need to divide it in two regions. The blue region and the green region. So the curve on the right is r is 2 cosine theta, and the curve above is r equals 2 sine theta. So let's do the blue curve first. The area of the blue curve will be 1/2 the integral. Well, let's see, this is sine theta, so it's going to be at the origin when theta is 0, and we'll get to the red dot when theta is pi over 4. And we're going to integrate 2 sine theta squared d theta. Now the green curve is the integral of the cosine, and that will go from, this is a pi over 4. It will go from pi over 4 until it gets back to the pole, which happens at pi over 2. And so now we can calculate this area. It's 1/2 integral of 0 to pi over 4 of 4 sine squared theta. And then remember that we'll need to use our identities for the sine squared and the cosine squared. And we'll multiply through again just to clear our denominators. And now it's time for the integral. And now we have to plug a bunch of things in. This is pi over 4 minus 1/2 sine of pi over 2 minus 0 minus 1/2 sine of 0. Pi over 2 plus 1/2 sine of pi minus pi over 4 plus 1/2 sine pi over 2. So we see that this is 0, this is 0, and this is 0. So this will equal pi over 4 minus 1/2 minus 0 plus pi over 2 minus pi over 4 plus 1/2. So if I combine all these, I should get pi over 2 minus 1 as my area. So what we see happening is we typically need to find where the curves intersect and then use that to find the area. So let's do one more example. Let's find the area in the upper cardioid, but not the lower one. So so that we have two graphs, r equals 3 plus 3 sine theta, and r equals 3 minus 3 sine theta. The graphs of those two cardioids should look something like this. Okay, and this should be the r equals 3 minus 3 sine theta, and this will be r equals 3 plus 3 sine theta. Okay. So we need to find where these curves intersect. So they will intersect when 3 plus 3 sine theta equals 3 minus 3 sine theta. So they'll intersect when 6 sine theta equals 0. That tells us they should intersect when theta is 0, pi over pi and 2 pi. Okay. So we're trying to find this area right here. So this point should occur when theta is equal to pi, and this point should occur when theta, sorry, the one on the right should occur when theta is 0, and the one on the left should occur when theta is pi. So we need to find the area of the outer cardioid, that's this curve, minus the area of the lower cardioid in that range of theta values. So this should tell us that the area is 1/2 the integral from 0 to pi of the outer cardioid minus the area of the inner cardioid. So we expand that, and we'll combine the two integrals. We see there's a lot of cancellation. And so this should just be the integral from 0 to pi of 18 sine of theta. And we should integrate that, and it should become minus 18 cosine theta from 0 to pi, which should equal negative 18 cosine of pi minus a minus 18 cosine of 0, which should equal negative, should equal positive 18 plus 18, which is 36. Okay, and here's an example for you guys to work on. Find the area common to r equals 4 sine of theta, sorry, 4 sine of 2 theta. R equal to 2. All right, so now let's switch gears and talk about arc length. The formula can be obtained in a very similar manner to the ones in the past, because we're using polar coordinates, but if r is equal to f of theta, we know that x is f of theta times cosine of theta, and y equals f of theta times sine of theta. So now x and y can be written as a parametric equation. And if you do all that work, you'll find that the arc length is equal to the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. Or in other words, it's the integral of r squared plus dr d theta squared d theta. So let's do an example. Let's do an example of the arc length of the cardioid on the interval from 0 to 2 pi. Warning, this integral will be a little bit tricky. So dr d theta is the cosine of theta. So this tells us that r squared plus dr d theta squared is 1 plus sine theta squared plus cosine theta squared, which is 1 plus 2 times sine theta, sine squared of theta, plus cosine squared of theta. These two make 1, so it's 2 plus 2 sine theta. So this tells us that our arc length is the integral from negative pi over 2 to pi over 2, 2 times it. So essentially, this cardioid should look something like this. So the arc length will be double what happens on the right side. So we're going to calculate that integral. It's not exactly in the interval, but you get the idea. And it should be the square root of 2 plus 2 sine theta. Now, I'm actually going to do a little work here. The sine function on negative pi over 2 to pi over 2 is the same as the cosine of theta on the interval from pi to 2 pi. Because the sine goes from negative 1 to 1, so the cosine goes from negative 1 to 1 in this interval. So this will be the integral from pi to 2 pi of the integral from 2 plus 2 cosine of theta. So we're actually going to use a half angle identity you can look up. And what this tells us is this integral is actually the square root of 4 cosine theta over 2 squared. Okay. So now we need to figure out, okay, that's the integral of the cosine, 2 times the cosine of theta over 2. But is it positive or negative? Because when you square something and take the square root, that's like taking the absolute value. And the cosine of theta over 2 is actually negative in this range. So this needs to be negative. And so this is negative 4 integral pi to 2 pi of the cosine of pi over 2 d theta, which is minus 8 times the sine of theta over 2, evaluated from pi to 2 pi. So that's negative 8 sine of pi minus negative 8 sine of pi over 2, which is 0 plus 8. And so 8 is the arc length of this cardioid. So here's an easier example that won't be quite so confusing. Find the arc length of r equals 4 sine theta over the interval from 0 to pi. Last but not least is the area of a surface of revolution. And this formula again will look just like the one we saw coming from the parametric equations. So if r is f of theta, Then we have two area formulas. We have f of theta sine theta. That's for when we rotate around the horizontal axis. Or x-axis. And we have a very similar integral when we rotate around the vertical axis. So we're going to do a little example. We're going to look at sine theta, and we're going to rotate around the horizontal axis. So our interval is going to be from 0 to pi. So the derivative is the cosine of theta. So the arc length, or the surface area, is from 0 to pi, f of theta, which is sine theta, times sine theta, because that's the formula when we rotate around the horizontal axis, times the integral of sine squared theta plus cosine squared theta. So we see that this piece just becomes 1. And we're integrating the sine squared of theta, which we know is the same as 1 minus the cosine of 2 theta over 2. This becomes pi times the integral of 1 minus the cosine of 2 theta. Which is then theta minus 1/2 sine of 2 theta. Evaluate from 0 to pi. So we get pi times pi minus 1/2 sine of 2 pi minus pi times 0 minus 1/2 sine of 0. And that should equal, well, this is 0, this is 0, this is 0, and it's just pi squared as the surface area. And so an example for you is to rotate the equation r is e of theta about the vertical axis on the interval from 0 to pi over 2. Let me know if you have questions, and I will see you in class.